Hey everybody, welcome back to Quantitative Reasoning. Today we're in section 3.3 and we're going to be looking at truth tables for negation, conjunction, and disjunction. Our objectives in this section are to use the definitions of negation, conjunction, and disjunction to construct truth tables, and we will also learn how to determine the truth value of a compound statement for a specific case. So here we go. So have you ever had anybody make a really complicated statement to you and you had to stop and think for a minute if their statement as a whole was actually true or not? So like you had to evaluate the truth of each individual component of their statement. Well, that's sort of what we're looking at today. So by determining when logical statements are true and when they're false, we will be able to draw conclusions from the data. And when we classify a statement as true or false, that's called assigning a truth value to the statement. So let's start off by looking at the truth table for the negation operation. So as you remember from a previous section, the symbol for negation is the tilde. So when we see something like tilde P, we actually read that as not P. And you remember that a negated statement has the opposite truth value from the original statement. We said before that the negation of a true statement is a false statement, and the negation of a false statement is a true statement. So that's what we see in the truth table here. So we have our statement P, and then in the next column we have not P. So what this truth table says is that when statement P is true, then not P is false, and when statement P is false, then not P is true. And now let's look at the truth table for a conjunction or an and statement. And you'll remember that the symbol for a conjunction looks kind of like an upside down V, and we read this symbol as and. Now the thing about an and statement is that it can only be true when both simple statements are true. So if we have two statements, let's say P and Q, there are 4 different cases that can occur. It could be that both statements are true. It could be that the statement P is true, but the statement Q is false. Or it could be that P is false while Q is true. Or both statements could be false. Now, for P and Q, which is the overall statement, if P is true and Q is also true, then the overall statement P and Q is true. If either part of the statement is false, then the overall statement is false. And if both parts of the statement are false, then the overall statement is also false. So again, notice that the only way P and Q can be true is if both components are true, otherwise P and Q is considered false. And this fits exactly with how we use the word and in everyday English. Let's take a look at a little example. So consider the statement, Mick visited London and he visited Paris. We could consider this as 2 simple statements. We'll call statement P the statement Mick visited London, and then Q will be Mick visited Paris. And there are 4 different cases that we have to consider here. So case 1 would be that it's true that Mick really did visit both cities. So if he really did visit both cities, then statement P would be true and statement Q would be true. So the overall statement, Mick visited London and he visited Paris, would also be true. And we can see that on the truth table here. If P is true and Q is true, then the statement P and Q is also true. Case 2 would be if Mick visited London but he did not visit Paris. So if he did visit London but he did not visit Paris, then statement P would be true, but statement Q would actually be false. And if that's the case, then the statement P and Q is also false. So when P is true but Q is false, the statement P and Q is false. So I just want you to think about this in terms of everyday English. If I tell you that Mick visited London and he visited Paris, but you know that he didn't really visit Paris, so that part of the statement is false, then you would consider this entire statement to be false. Mick visited London and he visited Paris is not true if we know for sure that the second statement is not true. Now let's think about what would happen if it's true that Mick visited Paris, but it's not true that he visited London. In this case, P is false, but Q is true, but the overall statement P and Q is still false because one of the components is false. And then in case 4, Mick did not visit either city. So if he didn't visit either city, then both P and Q are false, and that means the overall statement is false. So again, the only way for an AND statement to be true is if both components are true. Now let's look at a disjunction, and you'll remember that the symbol for a disjunction looks kind of like a V, and we read this symbol as OR. Now, a disjunction is true when either simple statement is true or when both simple statements are true. So take a look at it here. If both simple statements are true, then the statement P or Q is also true. If either component is true, then the statement overall is true. But if both components are false, then the overall statement is false. So let's go back to our same two simple statements where statement P is Mick visited London and statement Q is Mick visited Paris. But this time let's put those two simple statements together with an OR. So the overall statement is Mick visited London or he visited Paris. Now case 1, where he really did visit both cities, would mean that statement P is true and statement Q is true. And if they're both true, then P or Q is also true. So the overall statement, Mick visited London or he visited Paris, is true since both parts are true. And then let's think about case 2. So in this case, Mick visited London but not Paris. So if that happens, then statement P is true but statement Q is false. But still the overall statement P or Q is true. So think about it. Even if we know that this second part of the statement is untrue, the overall statement is still true. Mick visited London or he visited Paris is going to be true if either part is true. So the same thing for case 3. In this case, Mick visited Paris but not London. So in this case, statement Q is true, but statement P is false. But still the overall statement P or Q is true. Then in case 4, if Mick did not visit either city, then P or Q would be false. Because in order for an OR statement to be true, either one or both of the component statements has to be true. Now let's take a look at example 1 before we get into full-fledged truth tables. Here is example 1, and we're just going to evaluate whether each of these statements is true or false. So here we're given statement P is that 10 is greater than 4. Now we know that that is a true statement. And statement Q is that 3 is less than 5, and we also know that's a true statement. Okay, so let's look at statement A. Now statement A says P and Q. So now this is going to be a true statement if both components are true, because we know that in order for an AND statement to be true, both components have to be true. So P is true, and then we've got our AND symbol, and then statement Q is true. And so whenever you have true and true, the overall statement is true. Let's look at part B. So part B has not P and Q. Now we know that the not changes the truth value of this statement. So if P is true, then not P is false. And then we have our AND symbol, and then we have Q, and we know that statement Q is true. So here we have false and true, a false statement and a true statement. The overall statement here is false, because in order for an AND statement to be true, both components have to be true. Let's look at part C. So here we have P or not Q. Now we know that statement P is true, then we have our OR symbol, And then not Q is the opposite value from Q. So if Q is true, that means not Q is false. Okay, so now this is an OR. So we have true statement or false statement. Now we know that with the OR connective, the overall statement is true if one or both of the components is true. So one of these components is true, and therefore the overall statement is true. Then on part D, we have not P or not Q. So if statement P is true, then not P is false. Then we have our OR, and then not Q is going to be false because Q is true, so not Q is false. Now, again, with an OR connective, we know that it can only be true if one or both of the components is true, and here both components are false. So the overall statement is false. Now, notice what is happening here. We are able to look at each one of these compound statements and determine whether it's true or false based on P being true and Q being true. So we have no idea what would happen to each of these statements if P were true but Q were false, or if they were both false. Like, we would have to go back and do the whole thing again if one of these statements was false or if both of them were false. So if you need to fully analyze a compound statement and you need to know what would happen to this statement based on every possible truth value of each component, then you want to build what's called a truth table. So we're getting ready to do that. A truth table is just a table that shows us the truth value of a compound statement for every possible result of the component statements. So before we jump into building a truth table, let's just review our basic logic operations. As we know, a negation or a not statement has the opposite truth value from the original statement. And then the conjunction, which is an and statement, is true only when both component statements are true. The disjunction, or the or statement, is true when either or both of the component statements are true. So whenever we are asked to make a truth table for a compound statement, breaking the compound statement into components and using these definitions is going to help us construct the truth table. So here's how we do it. First, we're going to make a column for each simple statement, and we're going to put in column P true, true, false, false, and then in column Q true, false, true, false. That makes sure that we have all four possibilities covered, but also doing it in this order makes it easier for everybody to keep up with and know that we always have our answers coming out in the same order, because otherwise it would get really confusing and it would slow us down a lot. So just get used to the idea that for your first simple statement, you're always going to put true, true, false, false. And then for your second simple statement, you're going to put true, false, true, false. Now this next step depends on the statement that you're given. What you're going to do next is determine each column heading by reconstructing the given compound statement one component statement at a time. The final column heading will be the given compound statement from the problem. So you can have as many columns as you need so that you're not having to keep a whole lot of information in your head. So the number of columns you need depends on the statement that you're given. But after you figure out the column headings, then you're going to use the column heading to fill in the four truth values, looking back at previous columns as needed. So here is example 2 for us, and this one's pretty simple. It's not parentheses P and Q. So you can see that we've already got columns for P and Q, but what we need to do now is evaluate P and Q. So that's what will go here. And then the next column will be the whole statement, the not P and Q. But let's fill in our truth values first. So this is just an and statement or just a conjunction. So we know that an and statement is only true when both components are true, otherwise it's false. So on this first line here, where P is true and Q is true, P and Q is going to be true. On all the rest of the lines, it's going to be false, because on every other line, there is at least one false component. So false, false, false. Okay, now the next thing we need to do is put our column heading, which is going to be not parentheses P and Q. So this is going to be easy to evaluate because all we have to do is look back here. Not P and Q is always going to have the opposite truth value from P and Q. So where P and Q is true, not P and Q is going to be false. And then where P and Q is false, not P and Q is going to be true. So now that we've got our truth table filled in, we can see that not parentheses P and Q is only false when both simple statements are true. Now let's look at part B. So this one's very similar, but it has an or statement. So this one is not parentheses P or Q. So our first column heading will be what's in the parentheses. So that's going to be P or Q. Now we know for or statements, an or statement is true whenever one or both components are true. So here where P and Q are both true, P or Q is going to be true. On the second line, statement P is true, so P or Q is also true. On the third line, statement Q is true, so the statement P or Q will also be true. On the fourth line, both component statements are false, so the overall statement P or Q is also false. Okay, now that that column is filled in, we're ready to do the final column, which is the whole statement, not parentheses P or Q. So that's what we'll put here. And again, this is just the opposite of what we had in the previous column. So where P or Q was true, not parentheses P or Q is going to be false. And then where P or Q is false, not parentheses P or Q is going to be true. And now that we have the whole truth table filled in, we can see that not parentheses P or Q is only true when both component statements are false. Okay, here's example 3. So in example 3, part A says not P or not Q. So of course what we would want to do first is evaluate not P and not Q. And so those will be our column headings. And then our last column heading will be the entire statement, not P or not Q. Okay, now how do you think we're going to get the truth values for not P? Well, they are just the opposite of the truth values for statement P. So when P is true, not P is false. And when P is false, not P is true. And then we'll go on to the next column where we have not Q. Well, that's just the opposite of Q. So where statement Q is true, not Q is false. And when statement Q is false, not Q is true. So false, true. So you can see that each of these values is the opposite of the value of Q. And now we're ready to do our or statement. So we need to do not P or not Q. So we will only be looking at these two columns because these are the simple statements that are involved in our compound statement. So remember, an or statement will be true whenever one or both component statements are true. So right here on the first line where both component statements are false, the or statement is also false. On the second line, one of the component statements is true. Remember, these two are the two that we're looking at, not P or not Q. And so if either one of these is true, the statement not P or not Q is also true. On the third line, one of the components is true, so the or statement is true. On the fourth line, both components are true, so the overall statement is true. Let's look at part B. So part B is very similar to part A, except we have an and where part A had an or. So we still need to start by finding not P and not Q. So those will be our first two column headings. And then our last column heading will be not P and not Q. Okay, we already know that not P has all the opposite values of statement P. So where statement P is true, not P is false. Where statement P is false, not P is true. And then for not Q, it's the opposite of all the values in statement Q. So where statement Q is true, not Q is false. Where statement Q is false, not Q is true. And then we will work on the and statement. So not P and not Q is only true where both component statements are true. So right here on the first line, we do not have both component statements true, so that will be false. The second line is false. The third line, only one of the component statements is true, so that's overall statement is false. And on the fourth line, both component statements are true, so the overall statement is true. Okay, now we've got something a little different in example 4. So it says construct a truth table for the given statement P or not P. So our first column heading here will be not P, and then our next column heading is going to be the entire statement P or not P. So again, not P has the opposite truth values of statement P. So where P is true, not P is false. Where P is false, not P is true. Okay, now we know that an or statement is true when one or both of the components are true. So on each line here, one of the components is always true. So P or not P is going to be true on the first line. See, on the first line, statement P is true. And it's going to be true on the second line for the same reason. It's going to be true on the third line because not P is true. And it's going to be true on the fourth line. So what they've done is they've given us a statement that is always true. And you might say, well, why would we even need such a statement? What's the good of a statement that's always true? Well, you see these a lot in advertising. So for example, think about an ad for cereal or something that says, a diet high in oats may reduce cancer. Now, you and I hear that word may, and we think probably. So the way we interpret it in our mind, we're thinking a diet high in oats probably reduces cancer. But legally, that's not really what they're saying. By using the word may, all they're really saying is it either does or it doesn't. So what their statement really amounts to is they're saying that a diet high in oats either does or does not reduce cancer. Well, when you think about it that way, that kind of statement is always true. It either does or it doesn't. So in their advertisement, the statement they made here is true. No matter whether their cereal is good for you or not, it either does or does not reduce cancer. So this is a situation where one of the components must be true, and therefore the overall statement is always true. And this is called a tautology. A statement that is always true is a tautology. Another example of a tautology that we hear all the time is the statement, it is what it is. That statement really doesn't mean anything because of course it is what it is. I am who I am. Of course, there's no arguing with that. So it's an always true statement, therefore it's a meaningless statement. Okay, now let's look at example 5. So it says construct a truth table for the given statement. And here we have in parentheses, not P or Q, and then after the parentheses we have and not Q. So the first thing we will need in order to do this or statement is we will need to determine not P. And you could go ahead and do not Q next, but what I'm going to do is go ahead and work on the or statement. So I'm going to make my next column heading not P or Q. And before we do the rest of the column headings, let's go ahead and get the truth values for these. So we know that not P is always going to be the opposite value from P. So where P is true, not P is false. And where P is false, not P is true. So we've got those filled in. Now we're going to do not P or Q. So we're looking at not P or Q. Q is in this column right here. Now this is an or statement. So not P or Q is going to be true whenever one of the components is true or both components are true. So remember, just looking at these two, the column for P does not play a role here. So it's just not P or Q. So on the first line, the value is going to be true because Q is true. On the second line, the value is going to be false because neither of these components is true. On the third line, both components are true, so the overall statement is true. And on the fourth line, the value of the overall statement is true because not P is true. Okay, now the next thing we want to do is take those values and do and not Q. So in this column right here, I'm going to put not Q. And we can go ahead and fill these in because they are just the opposite values of what we have for Q. So where Q is true, not Q will be false. And where Q is false, not Q will be true. Okay, so now in the final column, we want the entire statement. So it will be parentheses, not P or Q, and not Q. Okay, so not P or Q is right here, and not Q is right here. And this is an and statement, so it's only true when both components are true, and we're just looking at these two columns. Okay, so right here on the first line, the first component is true and the second component is false. So the overall statement is false. On the second line, same thing. Only one of the components is true, so the overall statement is false. Third line, same thing. On the fourth line, both components are true, so the overall statement is true. Let's go on to part B. So we've got parentheses, P and not Q, or not P. So right here we've already started off with P and Q. So you can see in this first and statement we're going to need to know not Q. So let's go ahead and put not Q in this column. And then the next thing we'll do is we'll go ahead and do this and statement that's in parentheses. So this column heading will be P and not Q. Now let's go ahead and get the values for these two. So where we have Q is true, not Q is false. And where we have Q is false, not Q is true. So we'll just do that all the way down. And then for P and not Q, let's get straight which two components we're looking at here. So column P is over here, and not Q is right here. So basically you have to just ignore the column Q for right now. Let's just kind of put a line through it for just a minute. Okay, so we're looking at P and not Q. It's an and statement, so it's only going to be true when both components are true. So on this first line, P and not Q is false because one of the components is false. On the second line, both components are true, so the overall statement is true. On the third line, both components are false, so the overall statement is false. And on the fourth line, the overall statement is false. Okay, now we're ready for the next column. So we need to take these values that we just found and do or not P. So we need a column for not P. We'll put not P right here. And let's go ahead and fill in those truth values. So not P has the opposite value of P for every line. So where P is true, not P is false. Where P is false, not P is true. Okay, and then in the final column, we'll have the entire statement, parentheses, P and not Q, or not P. Okay, so we are working with the column P and not Q, and also the column not P. So we're doing P and not Q, or not P. Okay, so it's an or statement. It will be true if either component is true. So on the first line, both components are false, so the overall statement is false. On the second line, comparing these two components, one of them is true, so the overall statement is true. Same thing on the third line. The component not P is true, so the overall statement is true. And the same thing on the fourth line. And so this is the truth table for this whole statement. Now you get the idea, right, that the middle columns are basically our scratch work. They are us showing our work as we work step by step through the statement. But really, the truth table is just the original component statements and the final column is really all that matters. Now, so far, every truth table we've looked at has only had two simple statements, and therefore it had four different cases. So we always had statement P and statement Q. But if we have three simple statements, then we're going to end up with a much bigger truth table. So in this situation, whenever you have three simple statements, they're usually labeled P, Q, and R, and there are going to be 8 different true-false combinations. So what we usually do is we let the first column have 4 T's followed by 4 F's. So true, 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 false, 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 false. And then the second column will work the way the first column used to work. So it would be like true, true, false, false. It's 2 trues followed by 2 falses, followed by 2 trues, then 2 falses, till you get to the bottom of the table. And then the third column would have true alternating with false. So true, false, all the way down. And that way you get all 8 cases covered. And if you always have your truth values listed in this order, it's easy to compare your table with somebody else's and know that you have the same results. So again, it doesn't have to be done in this order, but it sure does make it easy to know that you've got everything covered and to be able to compare. So here is example 6, and what they've done is they've given us just a regular verbal statement here in English words, and we've got to break it down into 3 simple statements and then complete the truth table. So the overall statement says, I study hard and ace the final, or I fail the course. So statement P could be, I study hard. That would be one way we could state the first simple statement. And then statement Q could be the next part, I ace the final. And then statement R could be the third part, I fail the course. Now the way it's given here, I study hard and ace the final, in symbolic form would be P and Q. And then we've got a comma which separates the or I fail the course from the rest. So the comma indicates that these two parts go together. So we'll go ahead and put them in parentheses. Then we've got the word or, so we'll put an or symbol here. Or I fail the course, so that's statement R. So we've got parentheses P and Q or R. Okay, so here are our values for our simple statements already filled in, P, Q, and R. All right, so the next column heading is going to be P and Q. So let's go ahead and put that. And then after we get the values for P and Q, the next thing we'll want to do is use those values to do an or statement with R. So P and Q or R is what goes in the last column. Okay, now let's evaluate one line at a time. So we're starting with P and Q, so we're looking at these 2 columns. And P and Q will be true whenever both components are true. So on the first line, it's true. On the second line, still true. On the third line, it's false because one of the components is false. Fourth line, it's false. And the rest of the way down, it's false. You can see. The only 2 trues we got were up here where both components were true on these 2 lines. Now, when we take those results and do or R, now we're looking at P and Q in parentheses, or R. So here is P and Q, and here is R. Now this time it's an or statement. So this is going to be true whenever one or both of the components are true. So right here on the first line, both components are true, just these 2. Both components are true, so that's true. On the second line, we have a false and a true. So one of the components is true, so the overall statement is true. Third line, one of the components is true, so the overall statement is true. Fourth line, both components are false, so the overall statement is false. On the next line, we have one true component, so the overall statement is true. Next line, both components are false, so the statement is false. Next to last line, one of the components is true, so the overall statement is true. And then on the last line, both components are false, so the overall statement is false. And now part B says, suppose that you study hard, you do not ace the final, and you fail the course. Under these conditions, is the compound statement true or false? So if all of these things happen, was the overall statement correct? So what we'll need to do is we'll need to evaluate. So remember, statement P was I study hard. Now in this scenario, that statement is true because it says suppose you study hard, so that's true. And then statement Q was I ace the final. Now in this case, under the scenario that we're working with, it says you do not ace the final. And so in this case, statement Q is false. And then it says the last statement, you fail the course. So statement R was I failed the course. And in this scenario, that statement is true. So let's go to the line where P is true, Q is false, and R is true. And that would be right here. P is true, Q is false, and R is true. And in that case, the compound statement was true. So under these conditions, the original compound statement is true. So now, as you've noticed, a truth table shows the truth values of a compound statement for every possible case, but sometimes we don't always need every possible case. So if you just need to know the truth value of a compound statement for a specific case, you don't have to do the entire truth table every time. By substituting the truth values of the simple statement into the symbolic form of the compound statement and then using the appropriate definitions for not, and or, we can determine the truth value of the component statement without looking at the whole truth table, kind of like we did in example 1, if you wanted to go back and look at example 1. But here we're looking at example 7, so let's kind of do the same thing here. So it says determine the truth value for each statement when P is false, Q is true, and R is false. Okay, so in part A, we've got P and parentheses Q or R. Okay, now we're going to substitute the truth values in one at a time. P is given to us as false, so I'm going to replace statement P with a false. And then I've got my and then parentheses Q is given to us as true. So I'll replace statement Q with true. And then I've got an or. And then statement R is given to us as false. So I'll replace the R with a false. Okay, now we know we always work inside parentheses first. So this is an or statement inside the parentheses. A true statement or a false statement. And the overall statement is true because whenever you have an or statement, the overall or statement is true if either component is true. So I'm going to replace this whole parentheses with a true. That's going to give me false and true. Okay, now the next thing we're going to evaluate is the and statement. And we know that an and statement can only be true if both components are true. And so this and statement is false. So for these truth values, this compound statement is false. Now let's look at part B. So we've got not P or parentheses Q and not R. So just like we did in part A, we're going to substitute in the truth values that were given from the problem. So they told us that P is false. That means that not P is true. Then we've got an or. And then we've got parentheses Q. Now they told us that Q was true, so I'm going to put a true there. And not R. So they told us that R is false. That means not R is true. Okay, again, working inside parentheses first. This is an and. So I've got a true statement and true statement. And we know that an and statement is true when both components are true. So I'll replace this whole parentheses with a true. Okay, so then I've got true or true. And we know that an or statement is true if one or both of the components is true. So in this case, both components are true, and so the overall statement is true. So for these values, this compound statement is true. Then part C, we've got not, parentheses, P and Q, or R. So now remember, we have to work inside the parentheses first. So let's go ahead and copy in our truth values. We've got not, parentheses, statement P is known to be false, so I've got a false there. Then we've got and Q, statement Q is known to be true. And then I close the parentheses, and I've got my or, and we know that statement R is false. Okay, now working in parentheses first, we've got an and statement. Now we know that an and statement can only be true when both components are true. So this statement right here in the parentheses is going to be false because one of the components is false. So I've got not false or false. Okay, now we know that not changes the truth value. So not false is true. So now I'm going to take this not false and replace it with true. So it's going to say true or false. So I've got true statement or false statement. That means the overall statement is true because an or statement is true if one or both of the components is true. Okay, so for these given truth values, this compound statement is true. And then in part D, I've got not, parentheses, P or Q, and R. So let's substitute in our truth values. We know P is false, Q is true, and R is false. So I'm going to have not, parentheses, or true, close parentheses, and then the and then R is false. Okay, working in parentheses first. This is an or. Or statements are true if one or both components are true. So this in parentheses is a true statement. And so we're going to have not, and then this statement here will be replaced by true. So not true, then we've got and false. Okay, now not true amounts to a false value. So I'm going to replace that not true with false. So now I've got false and false. So I've got a false statement and false statement. The overall statement is false. And finally, we're going to look at example 8 together. I have part A on this slide, and then there's a part B on the next slide. So it says, the line graph shows living arrangements of U.S. young adults ages 25 to 34 from the year 2000 through 2017. Use the information in the graph to determine the truth value of the following statement. So let's take a look at this statement together. It says, it is not true that the percentage of young adults owning their own home is decreasing and the percentage living with parents is increasing. Or it is not true that in 2017, 11.9% of young adults lived with parents. So sometimes when you're dealing with technical information like this, it does happen that you can come across a really complicated statement and you need to determine whether that statement as a whole is true or false. And so what we're going to do here is break down this large statement into logical pieces and then use our logic rules to determine if the overall statement is true or false. So notice right here it starts with, it is not true that. So I'm going to let that represent a not in just a minute. But I want my statement to be actually the percentage of young adults owning their own home is decreasing. So I've got that right here. The percentage of young adults owning their own home is decreasing. And I have labeled that statement P. So make sure on your notes that you call this statement P. And then the next part of the large statement is the percentage living with parents is increasing. So I've got that statement here, and I've called that Q. And then the last part of this statement says, it is not true that in 2017, 11.9% of young adults lived with parents. Okay, the it is not true part, I'll let that be represented by a not symbol, but the statement that we will label is going to be the part that says In 2017, 11.9% of young adults lived with parents. So that's what I've got right here, and I've called that statement R. So you just want to make sure that you have the same three statements labeled P, Q, and R. Now what we're going to do is go back to the given statement and express it in symbolic form. So express it using P, Q, and R and any logic symbols that we need. So let's look carefully at it before we just start writing things down. So it says, it is not true that, so we know we're going to need a not symbol. But what comes next? It says, it is not true that the percentage of young adults owning their own home is decreasing and the percentage living with parents is increasing, comma. So everything that comes between the word that and the comma is being negated. See, all of this is affected by the words, it is not true that. So what have we got here? It says the percentage of young adults owning their own home is decreasing. That's statement P. And, so we'll need an and symbol. The percentage living with parents is increasing. And that's statement Q. So here we have P and Q. But in order to show that all of it is being negated, we'll need parentheses. So we'll have our not symbol here, and then in parentheses, P and Q. And again, the reason we needed the parentheses is because everything between the word that and the comma is being negated. And since it's more than one simple statement, we needed parentheses to show that the negation applies to the whole statement, not just the first part. Okay, then we have the word or, so we'll have an or symbol. It is not true that, so we'll have another negation. And then we have in 2017, 11.9% of young adults lived with parents. Okay, that's statement R. So here is our given statement in symbolic form. And now what we want to do is go to the graph and determine the truth value for P, Q, and R. So I'm going to go ahead and copy down our not, and then let's look at P. So statement P said the percentage of young adults owning their own home is decreasing. So here is the line that shows what percent own their own home, and sure enough, that line is sloping downward to the right. So it does look like statement P is true. So I'm going to have parentheses and then a true. And then our and statement, and then next we have Q. So Q said the percentage living with parents is increasing. So when you look at the graph, sure enough, the percentage living with parents, that line is sloping upward to the right, so it is increasing. So statement Q is also true. And then we can close our parentheses and have our or symbol, and then we have our not. And then let's look at statement R. In 2017, 11.9% of young adults lived with parents. So the lived with parents line is this bottom one here, and they've got it marked here because it would be difficult to read it exactly on this size of graph, but it says that in 2017, 22.0% lived with parents. And so it looks like statement R is false because statement R says that 11.9% lived with parents, and we can see from the graph that's not correct. So not false. All right, now let's work inside the parentheses first. So we have an and statement. So we have true and true. And we know that an and statement is true when both components are true. So this whole parentheses is going to be true. So now we're going to have not true. That whole parentheses turns out to be true. Then we have or, not false. Now, the next thing we need to do is evaluate these two negations. So we know that something that is not true is false. Then we have our or symbol. And then we know that something that's not false is true. So finally we have false or true. A false statement or a true statement. And we know that when we're doing an or operation, an or statement is true if either component is true or if both components are true. So our or statement is true if one or both components are true, And so here we do have one true component, and so the overall statement is true. And now let's look at part B together. So this involves the same graph, but this time the statement is different. So let's read the new statement. It says, in 2017, 22% of young adults lived with parents, or less than 40% owned their own home, and it is not true that the percentage living with parents is increasing. So again, these commas help us with the grouping the same way that parentheses would help us in an algebra statement. So we have in 2017, and that means that the in 2017 part applies to everything between these two commas. So when we write our compound statement, we need to keep that in mind. So let's label our component statements first. So statement P would be, in 2017, 22% of young adults lived with parents. So that's the first statement, so I just labeled it P. And then the next part says less than 40% owned their own home. But when? That can only be determined to be true or false if we know when. Well, that's why we have to understand that the in 2017 applies to both parts. So statement P was, in 2017, 22% of young adults lived with parents. And then statement Q can be, in 2017, less than 40% owned their own home. Okay? And then for the last part, we have, and it is not true that the percentage living with parents is increasing. So I will represent the it is not true with a not symbol, but I'll just let statement R be the percentage living with parents is increasing. Okay, so that's what I have for statement R. Now to get the compound statement in symbolic form, let's go back over here. So it says in 2017, 22% of young adults lived with parents, or in 2017, less than 40% owned their own home. So we need an or symbol. So we'll have P or Q. And then we've got a comma. So all of this gets grouped together. Everything that came before the comma is grouped together. And then we have and. So we'll need an and symbol. It is not true that. So we need a not. And then we have statement R. Okay, so we've got parentheses P or Q and not R. So let's go to the graph and determine if each of these is true or false. So for statement P, it said in 2017, 22% of young adults lived with parents. So here is the line that shows the percent living with parents, and it says that in 2017, 22% did live with parents. So statement P is true. Then we've got our or symbol. And then statement Q said in 2017, less than 40% owned their own home. So when we look at the owned their own home line, 2017 matches up with 38.4, and that is less than 40%, so statement Q is also true. Then we've got an and symbol and a not symbol, and then let's look at statement R. So statement R says the percentage living with parents is increasing. And again, when we look at the line that represents the percent living with parents, it is sloping uphill to the right, and so that's increasing. And so we'll put a true value on statement R. Okay, now let's analyze each piece. So inside the parentheses, we have an or statement. So it says true or true. And we know that an or statement is true if one or both components are true. And so this or statement is true. So I'll just put that as true. Then we've got our and symbol and our not true. Okay, now we know that not true evaluates as false. So something that's not true is false. So now I've got true and false. Okay, so I've got a true statement and a false statement. So the overall statement is false, because you know that an and statement can only be considered true if both components are true. And here one of the components is false. So the overall statement is false. Okay, we've done a lot of hard work in this section, And I know it might be different from a lot of what you've done in previous math classes, so it might take a little practice and a little getting used to the wording and the terminology that we use, but you can do it. And if you're having any trouble at all, practice, think. This section is called logic, so it does require a good bit of thinking, and it can't be memorized. You have to understand. That's what logic is. And if you're having any trouble at all, please reach out to your instructor as soon as you possibly can, and we will be glad to help you with whatever we can. So good luck, and I'll see you in the next video. Bye.